Today's video will demonstrate how to compute algorithmic efficiency. Hello, I'm James Helfrich. Efficiency is one of the most important metrics for determining the quality level of a given algorithm. The question is, what's the best way to compute efficiency? I mean, really, we could just compute by how much time it takes to complete the task, but that time depends upon many things, such as the speed of your processor, how much memory you have, other things that are running, and so on. A more deterministic way to determine efficiency is called algorithmic efficiency, and this is a function of how much the speed of the algorithm changes according to input size. This video will demonstrate how to compute algorithmic efficiency. Recall there are several levels of algorithmic efficiency. O sub 1, which is constant, which means performance is unrelated to the amount of input in the algorithm. Log n, otherwise known as logarithmic, and performance is a log of the amount of input in the algorithm. O sub n, linear, performance is directly related to the amount of input in the algorithm. N log n squared, and 2 to the n. So the question is, how do you assign a given level of efficiency to a given algorithm? Well, let's take a look at an example. First, we'll start with this flowchart here. The decision diamond is O sub 1 because regardless of the size of the input, it still takes the same amount of time. The prompt and the processing are O sub 1 because once again, we're going to visit each one of these exactly once, independent of the size of the input data. The read file, this could be O sub 1 if the data in the file is a fixed size. However, if the amount of data in the file is variable, then it's going to be O sub n, where n is the number of elements in the file. The decision diamond is O sub 1 because it takes the same amount of time regardless of the size of the input. Therefore, the overall efficiency is O sub 1 unless if the size of the file varies. If that's the case, it's O sub n. Let's take a look at another example. This case is pseudocode. So I'm going to have a range of 2 elements, 0 and names of size. This always has exactly 2 elements, so therefore it is O sub 1. Now here's a tricky one. While range of 0 is less than or equal to range of 1. Now both of these are indices. Now how many times is this while loop going to get executed? Well, we're going to have to take a look at how range of 0 and range of 1 get impacted. And we're going to realize that every iteration, these guys get progressively closer to each other in an exponential way. Therefore, this is O sub log n. In other words, if there are n elements in the names list, then it's going to be executed log n times. Now, just take a look at this return statement. Regardless of the size of the input, we can only hit this return statement exactly once. Therefore, this is O sub 1. Now, the other if statements are going to be O sub 1 by themselves because it takes exactly the same amount of time to execute a single if statement if there are 1,000 elements as it does if there is 1 element. However, this is in a log n loop, and because it's in a log n loop, this is O sub 1 times O sub log n, which is O sub log n. At the end here, we're going to loop through every element in the list. Now, since there are n elements, this is going to be O sub n. In other words, if I double the size of the list, this is going to take twice as long. Now, in order to determine the overall efficiency, I have to take the largest exponent for each of the different lines of code. So I have O sub 1 log n, O sub 1 log n, and n. Since O sub n is much bigger than the other ones, the overall efficiency of this algorithm is O sub n. Here's another example. This one is in C++. We're going to start with the calling of the function. Now, it takes the same amount of time to call a function, whether there's 1 element in the collection or if there's a million. However, passing the parameter, that could vary. Now, since we are passing the parameter by reference, that means we are not making a copy of the text, then this is O sub 1. However, we are passing this parameter by a value, and we were making a copy of text, then this would be O sub n, where n is the number of elements in the string. Now, how long is it going to take for us to iterate through every element in the list? The answer is O sub n, because we're going to visit every element exactly once. If there are n elements, that's O sub n. Now, the if statement, we are going to execute this if statement exactly once per iteration in the loop, and this if statement by itself is O sub 1. However, because it's in an O sub n loop, then this is going to be O sub n as well. Now, this one's tricky here. We're going to replace a single character, the less than, with the ampersand LT semicolon. In other words, we're going to have to expand the list to accommodate the 3 new characters, which means every element after the less than is going to have to be moved to the right by 3 elements. This operation by itself is O sub n. How many times will get executed? Well, now that depends. In the worst case scenario, a string that consists of nothing but the less than operator, then this will be executed n times. and therefore the overall efficiency would be n squared. However, if there are 0 or 1 elements in the string, then this will be executed only once. Therefore, the overall efficiency is going to be O sub n squared. We have 4 different costs here, O sub 1, O sub n, O sub n, and O sub n squared. Now, the n squared is going to dominate because it is the most expensive of the bunch, and therefore the overall efficiency is O sub n squared. Now, just to see how this works, imagine there was 1,000 elements in the collection. The O sub 1 will take, well, 1 unit of time. The O sub n will take 1,000. The O sub n will take 1,000. The O sub n squared could take potentially 1,000,000. Since 1,000,000 is so much bigger than 1,000, or 1, the largest exponent dominates the equation, and therefore the overall efficiency is n squared. And of course, the worst case scenario is when the string consists of nothing but the less than operator. This is example 3.1, 3.2, 3.3 in the efficiency chapter of the software design textbook.